Ladies and gentlemen, very good morning, Atlas. I have my pleasure and my honor to introduce Professor Atlas Wang, who is a tenured associate professor and holds the Temple Foundation endorsed by Faculty Fellowship number 7 in the ECE department at the University of Texas at Austin. Beside that, he is a full-time research director for XTX Markets, heading the new AI lab in New York City. Dr. Wang has a core research mission to leverage, understand, and expand the role of low dimensionality in machine learning and optimization, whose impacts span over many important topics, which could be very long listed. Most recently, we have also learned that Atlas is one of the 100 people who are shaking the world and turning it into the right direction. I do believe that you all be turned to the right direction after listening to his wonderful keynote. Atlas, very glad to see you here with the keynote. The floor is yours.
All right, thank you so much, Vadim. So first, I'm neither very sure about shaking the world, nor very sure about the right direction, but I hope I can try. And again, I would like to thank you for having me here, especially for giving talk to the UCU audience. I have told Vadim that I would really have loved to visit Lviv because 6 years ago, I actually wrote a paper together with UCU researchers, and that remained one of my best cited papers and one of my favorite ones. I have promised to give a visit to Lviv. I hope I could make that thing soon. And for today's keynote, I want to talk about one of my university work done about the efficient inference of large language models. I'm doing this presentation with a list of outstanding collaborators with Zhenyu, my PhD student, Beidi from CMU, and Yuandong from Meta, and a long list of other people from collaborators from UT Austin, Stanford, UC San Diego, Berkeley, Adobe, Meta, and CMU. Well, the list of participants reflect how interdisciplinary and diverse this project is. Actually, it's a synergistic effort between people who do algorithm, people who do theory, people who do system and hardware. So I'm really liking this work. Although I have too limited space on this page to display the full list. You know, as Fermat correctly pointed out 400 years ago, I have a marvelous demonstration of list of co-authors, but this margin is really too narrow for me to display. But I promise you later I will give them the credit to show up. Let's start from something probably not well known to people. Large language models are very useful. I suspect I will not get a dispute here. And also, it's very expensive. That's probably also globally agreed upon, right? So there are many reasons that make our large language models expensive. So for example, everybody knows that language models are large and 7 billion, 16 billion, 450 billion, and who knows how many billions the GPT-4 we're talking about, right? So large model size is definitely a thing. A second inherent reason is the attention layer's quadratic complexity, because it needs to compute the pairwise similarity, essentially, between any of the two tokens. So for a long window of size L, the computation complexity will scale with L squared. And that will become very quickly become unaffordable when we pursue the real long context lengths. For example, GPT-4 and Gemini are all not talking about the millions of tokens. So we're talking about a million square of the pairwise similarity computation. That's another well-known thing. But today I want to talk about a third point that has hurdled the language model's efficient inference. That is called KV cache. KV cache is a special system structure that is designed to store the intermediate attention key and value doing autoregressive generation. If you haven't worked on that, let me explain that to you. Consider that we're generating a sequence from language model. We are always generate, for all the current mainstream model, we generate in a fashion we call autoregressive generation. That means we first generate word 1 and then generate word 2 based on word 1 and word 3 based on word 2, etc., etc. And as I just mentioned, the key of this generation is the similarity, pairwise similarity computed by self-attention. And the way they use to compute similarity is to project each token into actually three values: key, query, and value. And so the query and the key are used to compute similarity, and the value are then being reweighted by the computed similarity. So essentially, each generated new token could be considered as a non-linearly reweighted version of all past tokens values, and the reweighting coefficient is decided by query and key. Here you may notice one special property. When I have to generate a new token, yes, sure, I need to generate a new key and value for this new token, for sure. But the query and the key and value for the past tokens, they don't have to change because I don't have to recompute the similarity of all past tokens. They are not affected by the new generation because my sequence always go from the left to the right. So the left is once they are generated, they're done, the ink is dry. Their similarity could be reused. Similarity computation by self-attention could have been reused in generating the next token. So if we don't reuse them, then we're talking about, say, if I generate a K, I have to generate a similarity matrix with a K by K size. And then I generated the K plus 1. I have to recompute the matrix of K plus 1 times K plus 1 size. But now, by recognizing the similarity computation between past tokens can be reused, we don't have to regenerate that K plus 1 times K plus 1 matrix. At least its K plus K submatrix could have been reused. And that is a very big saving for computation speed. Otherwise, every token, if you now use GPT, and if without this autoregressive generation, you will see the more you generate, the slower your GPT pop up the next token. And that would be horrible if we scale up to million level size. So KV cache is a very good strategy for optimized inference speed. But what is the price you pay here? That you have to cache the past key and key and values generated because you will need to reuse them for generating the future token. So after you generate the current token, its key and value, those what self-attention need have to be retained in the memory because they will be reused many times in the future. And when you go further and further into longer context, the number of key and values you have to restore become more and more, and eventually become very prominent memory cost. Let me give you an idea how prominent. For a 30 billion parameter language model, which nowadays we don't even call that very large, and with a batch size of 128 and the average sequence length of 1024, those are all very standard numbers. Guess what is the KV cache cost to generate one sentence of 1024 words? That would be 180 gigabit of KV cache. So if you make a comparison, some of the best GPUs on the market that customers could buy, for example, H100, A100, their best offered GPU memory is 80 gigabit, in contrast to 180 gigabit of KV cache. That means if we don't do anything to optimizing KV cache, if you only have one GPU or two GPUs, they're already NVIDIA's best offerings. One or two GPUs cannot even run an inference of the latest model, and I haven't even been talking about the training yet. So this is a research challenge. KV cache is essential for fast generation, but it causes memory bottleneck. So, and our research goal is to reduce KV cache memory without affect its speed and its accuracy. I hope I'm making a convincing case why we have to do it. So what have been done before our work? There are a lot of work, of course, in reducing the cost of attention, but they all more or less are off the topic from the KV cache. I mean, before our ones. So you will find a lot of high impact works in overcoming the quadratic memory complexity in attention, reformal, performal, or from the hardware level flash attention. They all make attention more memory efficient and computed more costly on hardware. But they do not directly touch KV cache. Any efficient attention will still require you to keep the past cache of K and V, key and values, as long as it still follows autoregressive generation way. There has been other works that try to specify carry cache or use multi-query to reduce the cache size. But what we have found is this comes at a heavy price of generation quality. You will have a lot of high miss rate. Miss rate here be defined as being the truly important words are being dropped when you clean carry cache, but they should have been retained for generating in the future. We'll talk about it later. And there were some more recent works talking about how to directly compress the carry cache. But for example, gisting tokens or landmark attentions. The rough idea of those work is they were trying to learn a mapping between past carry cache into a condensed representation, such as using one token to represent the past token. So essentially, I'm learning a summary of my carry cache, and those two works, gisting and landmark attention, both last year, are pioneering works in that way. But the caveat here is, in order to make those methods to have effect, you will need to relearn the language model in order to be adapted to this summary token. In other words, their carry cache compression or evasion policies are expensive and cause some relearning. If you want something that could just work on the fly without any retraining, they are not your choice yet. So what I would be wishing for if I could write a wish list for Santa for my Christmas gift for good carry cache. And here's my wish list, ideal carry cache. Number one, it would be small for sure. Number two, I want to be accurate. And in our term, we say a low miss rate. Low miss rate here means I could correctly identify the important words for future words generation even before I generate the future word. So I want to predict what are important and try not to hurt this part of this part of memory cache in KV. And you must remember that the injection of carry cache is a no regret process. Because in hardware, if we have cleaned that carry cache and leave new empty space for future tokens to come in, that carry cache is erased and erased forever. You cannot say in the future, dang, I have erased the wrong carry cache, wrong token. I want to bring it back. No, this is not possible in real hardware implementation. So you have to make a decision without having complete information, and you don't have a power to regret. The third thing is the carry cache, as I mentioned in the last page talking about the gisting and landmark. The injection policy, the policy to compress carry cache size, cannot be expensive by itself. Because remember, why we use carry cache? It's because we want to accelerate the autoregressive generation by maximally reusing the computation. And if our carry cache injection is more expensive even when generation itself, then we are beating our own purpose, right? So small, accurate, and low cost by itself. Those are my wish list for carry cache injection. And I want to do that on the fly while maintaining the generation performance. How could possibly do that? So let's start from a few observations that has been underlying our proposed method. I'll tell you three things. First, in attention, there is a very prominent sparsity pattern, and that is a ground for the possibility of small cache size. Let me explain. So we have tried a few pre-trained LLM checkpoint and try to observe the attention magnitude pattern. As I said, so every generated new token could be considered as the past token's value reweighted by a similarity value computed by them each other. So if you are familiar with the kernel representation, attention could actually be considered as a form of kernel. And so we look at all those pairwise similarity computation because they are my coefficient. And I find that those pairwise similarity computed by attention are extremely sparse. Here on the left, we have computed we have computed the attention sparsity defined as the following. For each layer, we'll choose the highest attention score value, softmax Q times K transpose. This is my so-called kernelized version of the similarity computation, which is also the implementation of attention plus a normalizer factor. So I computed all those values in a layer, and we use the maximum layer times 1% as a threshold. Lower than this threshold, I would call it 0. I use this way to compute an approximate sparsity of each layer attention. And guess what? In almost all layers, the sparsity computed in this way is over 95%. And in some layers, it can get very nearly to 100%. Only a few of the combinations are in effect when generating the future token. So what does it mean? It means in a large vocabulary of the words, every new words generation, it's naturally impossible to take a look back to all the words in my past. Like I have so far been talking probably thousands of words since the start of this presentation. How many words do you think are relevant to the current words I'm speaking of? It's a very sparse correlation. You are supposed to have this sparse correlation because your vocabulary space is too large. Sparsity comes as a natural consequence of over-complete representation. If you come from a wavelet or dictionary learning world, you are probably already very familiar with this concept, over-complete representation. So, okay, practically here, since we discovered the sparsity of coefficient, the sparsity of attention similarity / coefficient, then we realize that you do not have to access all previous key and values in generating the next token for each of the token. Because of the sparsity, most of the token pairs are irrelevant for generating the next. Just a few ones with the prominent sparsity will be needed. All right, so that is one blessing. We know that ideally, it's possible to select a sparse subset for generating each token. What is our next question? But this observation, remember, this observation will be useless if we find the important sparse subsets for tokens are different for every next future tokens. Because I said, if I want to give up on a token, I erase that from my KV cache, it's impossible for me to regret. So if one token are deemed as unimportant for generating my word K, I decide to erase it. And then come to word K plus one. K plus one say, hey, that word is so important for me, get it back. No, that's impossible. So we cannot afford the price that if every token is rely on sparse subset of words, but a dynamic subset of words. So do we have that luxury? That comes to the second observation. We further try to observe what are those heavy hitters over a natural language word set. And we discovered the second observation we called parallel distribution of pairwise word similarities. And I invite you to look at the left figure. So in the left figure, we have, let's first, we do the following. For one pre-trained language model, we get its vocabulary and the word index, the index of each word, including the vocabulary, are on the x-axis. So we first computed the attention scores of every token with all other tokens. That is computed by the following. So I run my pre-trained large language model over a large language data set. And for each word appear, I will record its attention with other words each time. And I will then sum all those attentions this word have ever generated to any other words in the vocabulary together. And I will call it accumulated attention for this specific word over this large language vocabulary. And I could do that for every word. So every word would have an accumulated attention score once I finish the one dataset inference. I want you to, let's pause a moment and think what this accumulated attention score means. If a word have a high accumulated attention score, that means this specific word tend to interact very actively or very prominently with other words, regardless of what words are, but over the entire dataset, for all other words in the same vocabulary, this word is a social queen. This word is very actively talking to other words during the generation process. So we would call it a very social word, right? And in this plot, represented by those red scatter points. Those very social words should correspond to those on the right left, on the top right, because look at this y-axis, those are the co-occurrence times, and this side, the accumulated attention scores, those very social words are on the top, means they have a very high accumulated social attention. And this is what this red scatter point look like. And what is the left? We further try to make sense what have caused some words to be very social with the others. If I could pause here for another moment and ask, just recall your experience writing an English article. What are the words you will use the most? You will probably not use your professional jargon a lot. You will probably not use your fancy words a lot. What are the most common words you will use? The, to, by. Those most common words needed by almost every sentence everywhere, those are the most common thing you will use, right? So indeed, we have did another statistics in the same vocabulary. By looking at those raw language, which token tend to be used with all other tokens in the same sentence. And if one token are used with other tokens in the same sentence, we would count any other token in the same sentence, we'll call it a co-occurrence. And again, we do that over the entire data set, and we call it co-occurrence times. Very interestingly, we find this gray curve representing the co-occurrence of words with other words in the vocabulary strongly correlate with the accumulated attention scores. So you are looking at this gray curve with this scatter point in red dot. So what we learn from here is there exists a small set of tokens that are constantly more social than the others during generation. Those are marked by the high attention score ones, accumulated attention score ones on the top right. And one reason for those tokens to become social is because those words are also highly likely to co-occur with other words. Those are frequent words used by Allen context and Allen sequence. So that strong correlation implies that we are able to find a common subset that will be reused by every new word generation. We call that heavy hitters in our context. And those heavy hitters with a high accumulated attention scores could be estimated from the co-occurrence time in the raw language, raw vocabulary. So this is so that shows that there exists such a static common sparse set, and this is naturally because the long tail distribution of vocabulary usage in language. That's the second good news. We not only have a sparse set for each token, but different tokens' desirable sparse set may be largely shared due to this long tail co-occurrence property. That's my point 2. Point 3. Before I enter my point 3, let's first prove our concept. Sorry. Are those heavy hitters really critical for my performance? We just verify that there exist some tokens with very, very high attention score. There exist some tokens that always social with others, but are they directly related with the performance? This page gives us an affirmative answer. We do 2 sides of experiment. On the left, we tried to erase the heavy hitter tokens during the generation performance always. And what you see here is compared to the baseline, it would almost destroy our performance, sometimes lower than 20% of the original performance in all the tasks we have tested. So heavy hitters are important. We actually have other comparison experiment in paper show that if you randomly erect tokens, the performance loss will be much more mild, roughly here. And on the right, it's another experiment showing that if we only keep heavy hitters, the performance, heavy hitters, the performance, you can see you can look at either this red line or the blue line. The performance could be largely preserved compared to the baseline, which use all the tokens. So you can see that the red or blue line, they're almost coincide with this green dot in 6 of the dataset we have tested, but greatly surpass the local baseline, which means if we just use the nearest few tokens, and if we match the nearest token number with the heavy hitter we kept, the performance are there is a visible performance gap across. So with this two sides of experiment, we prove heavy hitters are indeed critical for performance as well. They are not just a phenomenon, their performance are highly correlated. Now let's take a look back of my Christmas wish list. What I want from my ideal KV cache. I want a small cache size. Is that possible? Yes, that is possible because we know that now each token only rely on the very sparse subset of attention or KV to be generated. And I also want this subset to be consistent over each token generation. That has also been verified concept. There is a strong dataset level, population level, the distribution of heavy hitters and not. And I also want to show that those heavy hitters alone are enough to preserve performance. And that has been showcased by last page. Keeping that small set of influential tokens are critical enough for maintaining most of the performance. Great. So I have already done my version 1, I already clicked my item 1 and 2 in my wish list. Now let's look at my item 3. I would like a low-cost injection policy to reduce the workload time. And this is not achieved yet because all the previous thing I have been telling you how to find those heavy hitters is to compute the accumulated attention scores across the entire dataset and then decide which one to discard. This is a good proof of concept, but totally useless for practical generation because I cannot first run your entire dataset and then give a non-important weight to each token, then generate again. Then what's my point, right? I have already paid the price for the API. So we would need to find a lower cost injection policy that does not rely on global statistics of attention score. And the good news here is that is also possible, like I will discuss next. Rely on greedy decoding and local statistics are provably effective for retaining the heavy hitters as well. So this is our punchline that our heavy hitters, what we can achieve. We show that using heavy hitters, we are able to improve the throughput of the 3 leading commercial inference systems, Microsoft DeepSpeed, Hugging Face Accelerator, and MetaFlexGen, by up to 29 times of memory cost, and further reduce their latency by 2 times, and no visible performance degradation. This is a claim we made by last year's News when this paper was published. For now, heavy hitter was almost incorporated in. I think it's incorporated in all the 3 inference ranges already. So we are not competing with ourselves now. I'm talking about competing with those 3 engines roughly 1 year ago. And this is, as I promised, the full author list of people, and the paper can be found in News 23 proceeding. All right, so since I have prepared the background so far, there is only one major thing for me to discuss about heavy hitter now, technically. That is how to compute in a locally greedy way without relying on the global set statistics. The algorithm is actually surprisingly simple. We, as heavy hitters, exhibit importance for future generations. We want to, as we generate the token autoregressively, we want to inject the non-heavy hitter KV embeddings. So we can expect, in that way, we can expect a small KV cache and no performance degradation, right? So but when I generate, you can see here as I illustrate, when I generate a token 4, I have only access to generate a token 1, 2, 3. When I generate token 5, I get only access to 1, 2, 3, 4. I don't have the full access to the global statistics. How to determine those heavy hitters during this autoregressive process though? So here, let's look at this illustrative example together. This figure represents the attention process during generation. And the metrics are in the yellow box means the record of attention scores in all previous decoding steps. So all say similarity scores. And in this table, each row, the ith row means the attention score of the ith decoding step. So that's why you can see by each row, the sum of the scores are equaling 1, because for each row, we are computing eventually a normalized probability distribution on the similarity scores. So each row will be added together to 1, but not each column. What we have to compute here exactly is each column's sum. because each row is this token's weight in generating token 1, token 2, token 3, token 4. So token 1 will only rely on token 1. Token 2 will rely on token 1, token 2, and token 3 and token 4. That's why you see this matrix to be lower triangle. But now let's look at this each column. What does each column mean? So let's look at the first column, represent the token 1. So the token 1 has a weight of 1 in generated the first token itself, has a weight of 0.01 in generate the second token, 0.01 weight in generate the third token, 0.2 weight in generate the fourth token. So if I add all those weight together, those will be the accumulated attention score we have been talking about. This is the total weight this token has played together in generating all the 4 words we have generated so far in this sentence. So when we talk about accumulated attention score, we want to compute the summation of attention scores by column in this attention table. So let's do that. And so those are the summations on the top. Now let's assume we have a pool budget size of KV cache equals 3. So when we generate a token 4, we have 1, 2, 3, 4. 4 group of K and V's need to store. So we have to give up one of them. Our algorithm tells you just be greedy, which means I have the current attention scores. Let's just look at the accumulation attention score for my 4 candidates. Token 1 give 1.4, token 2 add to 1.5, token 3 add to 1.5, and token 4 is by itself 0.6. I will just compare those 4 numbers and greedily drop the column which have so far the lowest accumulated attention score. So this seems to be a brutal greedy adaptation of what we said in the global case, right? In the global case, I would have run the entire inference and accumulated the attention score for everybody until the end of my generation. For now, I do that along the way on the fly. Yes, it's indeed that simple. You can see that those. If we decide to generate, based on our algorithm, at the end of decoding step 4, we want to erase the token 3's column, so this becomes empty. And as we said, once it has been erased, we no longer have access to that in the future generation. That was indeed the case when we generated token 5. Now look at here. So token 1, token 2, token 3. So token 1, token 2, the first 4 rows are still remain the same as the above table. But token 5, you're recomputing its own probability distribution. So with token 5, you are able to compute, you are able to add a new element to token 1, token 5, token 2, token 2, and token 4, the 3 surviving members column, and recompare their accumulated attention score, and then compare also with the latest one added, and decide which one to abandon at this step next. So the unfortunate guy this time is token 4. So you can see that by this greedy process, at any step of decoding, I will only hold 3 group of the three tokens KV embeddings by dropping those who do not have the high enough accumulated attention scores, and this could be done in a total greedy way. Well, there are more system implementations to make this actually work. For example, to ensure the I/O efficiency, well, after we have dropped those columns, we do not swap memory when the KV is evicted. We just directly fill the newly added KV in this column. This is actually a tricky step to make sure we don't have the overhead or reindexing table, but those are the detailed things. If you are interested, you can look at our codes. So it may look too brutal, right? Just to do the global thing local, and it does not always work. So should we expect it to work? Let me provide you empirical evidence first and theoretical evidence next. In empirical evidence, we have indeed done the comparison between our proposed local way and the practically infeasible but supposedly optimal global way. So we run another baseline by indeed first finish inference on the entire dataset, compute attention score for each token, and then do the inference again, but now use a materialized attention score accumulated over the entire generation process. So this has no computation saving at all compared to our local. This is actually more expensive because it has the inference twice. And this compared to our decoding step is listed here. The global statistics are illustrated using this red curve. Sorry, it's the same figure I showed a few pages ago, but I intentionally didn't tell you the difference between those two red and blue curves. Now I can tell you. The red curves are the one using the impractically computed global statistics. And the blue one is our proposed algorithm, which means I only use greedy step to discard the tokens on the fly. You may be surprised to find that the global statistic and the local statistic based on greedy decoding have almost identical performance, but only the local one will give you the compute benefit. And both performance are close enough to the baseline and stronger than the method that only keep the k most recent tokens, essentially using a smaller context window. But why this is feasible? Now this is and this comes to the stage of the theorists in our group. So we are able to show that we present the concept of a submodular property, which basically means diminishing returns in a set function when elements are being included. We are able to show that our greedy evaluation policy is actually a reformulation of a dynamic submodular maximization problem. By assuming the attention scheme to be submodular, we could establish that our greedy policy is near optimal to compare to the global optimal evaluation solution when the context length, when the cache size is very large. So it's called asymptotic limit. So there is a theoretical guarantees, and the details of the proof can be found in our paper. But basically, that echoes our empirical finding. Local evaluation is as effective as the global evaluation by some optimization reformulation. I'm skipping the detail here, but welcome to check our paper. So now we have clicked all the three pieces in my wish list, right? I want the cache to be small. I want the performance to be minimally damaged. And I want the evaluation algorithm itself to be very lightweight. The evaluation algorithm we just introduced is so lightweight, right? Just at each step, computer update the accumulated attention score table and then give up those who don't have enough attention score, nothing else. How does it work? Let's now look at some empirical evaluation. We first on this page shows that heavy hitter oracle can reduce the memory footprint of KV cache by up to 5 to 10 times without any accuracy degradation on a wide range of model architectures, OPT, Llama, GPT-Neo, GPT-2, GPT-Neo X, and also different model size and different evaluation tasks. For example, on the top left is XTAM, which is a text summarization task. We use a Rogers score to evaluate the quality of the generated summarization. With nearly 20% of the KV, so the highest dashed line in dark color is the accuracy you can achieve with Llama on text summarization with a full cache size. So you see this is the top baseline and the empirical best performance. And the light blue curve is our performance heavy hitter oracle with a smaller and smaller KV cache budget. Can see that as low as 20%, which means we are forced to reduce to discard 80% of the past tokens because of KV cache limit. Based on our greedy online KV injection policy, though our performance is still as good as the full performance while only using 20% of the KV cache. However, if you naively shrink the context window by this model by 20%, essentially means using only 20% most recent tokens, the performance will drop by more than half compared to our smart attention score informed policy. And this tendency is remaining consistent for other tasks and dataset as well. So this page is about the memory. How about speed though? We will also want to show that our evaluation policy is very light in computation, which indeed And with the correct system implementation, it will not add any inference speed overhead, but because of the faster data movement due to smaller KV cache size, it should have accelerated the throughput. It's indeed the case, too. We conducted our experiment on NVIDIA T4 GPU and NVIDIA A100 GPU. So both, one is on the lower end, 16 gigabit of memory, and one is on the higher end, 80 gigabit of memory. So we implement our test framework on top of FlexGen, which is a standard in this field, and evaluate with OPD models. Well, we have tested a wide range of cases. For example, different lengths of prompt, different lengths of generation requirement. But overall, if we just skip those details, the main message we want to pass is, while we can reduce our KV cache budget by only 20% of the original, we can also achieve 3 times, 39 times, 29 times, and 29 times higher throughput. Throughput means the numbers of tokens the engine could have generated per second, compared with 3 leading engines, respectively. So we have reported those results to all those engines, and they have adopted our method as well. Oh, I also want to highlight heavy heater being a conceptually very simple method, could be incorporated with all other your favorite attention cell, efficient attention, or model compression tactics as well. For example, we try to combine KV cache with other self-sparse attention being developed in parallel. Like some people would just use a local token, local tokens during generation. This is which correspond to a form of static sparsity, which means here, okay, when I generate a next token, next token, next token, so each row, again, following the same format, each row is about which past token I'm looking at when generating this newer token in darker color. So every time when I generate a newer token, I'm only looking at this token and the past 2 tokens. This is called a local attention, a special form of static sparsity in attention form. And there are also people who try to use static attention sparsity by assuming a diluted sampling pattern. And we compare both of them by using static attention pattern here, plus the heavy heater attentions we are able to pick up. So besides the most recent ones, we also add some important heaters that are not the nearest, but deemed to be important. And what we have found is our method is able to improve the standard sparse attention by up to 35% of performance, and we sell, but while sticking to the same 20% KV cache. So it shows how plug and play we are with other attention saving methods. I want to show you some interesting and actually unexpected quality benefit we observed by heavy heater also, the heavy heater zone. I guess when you talk about efficiency method, you say model compression, efficiency generation, people's first reaction is, oh, okay, it makes me faster, but it also sacrifices me some model performance quality here or there. Actually, not necessarily true in model generation. I invite you to look at this example. So apparently I'm asking 2 language models, OPT and Llama, to write some poem for me. Okay, so this is a requirement. Ask a lot of life truth-seeking question, which I also ask myself every day. So this OPT is a 4 generation. Let's read this together, okay? Because it's really interesting. OPT is a generation about a poem. I have been thinking a lot about natures of consensus. I have been thinking about the nature of self, nature of the universe. I've been thinking about the nature of the self and nature of the universe. I'm thinking about the nature of the self, okay? Well, do you call that really poetic? I would say this looks like a homework I received from my student. I cannot say this is wrong. This is just boring, right? And surprisingly non-verbals in word usage. And now let's try to ask OPT to generate on the efficiency constraint. If I constrain OPT's cache usage to be 14%, this is what you get. It's totally nonsense. OPT totally have lost any meaningful generation property. And when you look at the OPTs and generation with the same cache constraint, but using our cache injection policy, H2O, here's what you get. The universe is a vast and complex place, and yet it's also a simple place. It's a place of order and beauty. It's a place where we can find our self-own answers. I'm a seeker, and I have been since I was a child. Well, if you compare this one with the original OPT generated one, who has written a better poem? I think you have an answer, right? I don't call this as this is a word level, but this is probably a better homework I would give grade to. This heavy hitter one. And a similar result could be replicated on generation, especially creative style generation using Llama model. Well, again, some context for you to write poems. This is what Llama generated. I was in the middle of moist, or not alone, surrounded by community trees, issue with union, blah, 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 blah. You can read by yourself, okay? I mean, again, this is okay, but this is a bit on the plain side. And if I restrain the cache size Llama could use, same phenomenon. Such creative generation tasks seem to be extremely sensitive to cache size, and if you to kill the cache size, you get you get nonsense after a little bit of text. A little bit better than OPT, but still. And with the cache limitation plus H2O generation, I feel again I'm getting a better point. I was in the middle of the forest, but I'm not alone. I was surrounded by the spirit of the forest, and they were watching me. For example, I like the spirits of the forest better than a community of trees because it clicks the word again of the forest and further emphasize the interaction between I and the forest. I think this is what this is a better poem would do. And they are watching me. And I feel a gentle breeze brush against my cheek. And I open my eyes to see a small white flower I reach out to. And if you also compare the word usage between the original model and the cache limited H2O version of the model, I would also say the word usage in this version or this version compared to this and this version is more verbose, more gentle, and more subtle. And so that comes actually totally to our surprise when I was playing with our models. Why after cache compression, the generation quality improves rather than decrease? We do have some hypothesis why it happens. In fact, it has been observed that those large language models have suffered from a phenomenon called over-smoothing during the intermediate generation process. That means due to their optimization being so complicated, in the middle of the layers, it's very easy to see different tokens become more and more similar to each other, and they tend to be decoded into similar words. That is why when you look at this and this generation, you will have an intuitive feeling that their word usage tend to be more self-similar, right? They lack verbosity. But after you have dropped the sparsity in by using heavy hitter approach, every word are requested to choose only the importance tokens rather than give uniform attention to all the custom tokens. That is actually an enforcement of diversity. Because I explicitly ask you, no, you cannot use a uniform reach out to pass the tokens. You have to do sparse selection. Then every token are forced to select who are most important contextual word for me in generating the next token. Every word need to make that choice. And that seems to implicitly boost generation sparsity. We actually have some follow-up paper to demonstrate this more formally. All right. Next question I want to invite you to think together with me is a heavy hitter a feature or a bug? So, well, that's a question I'm not sure if someone already get when I tell you what are the most heavy hitters. Well, I say that those are the most common English words. Are, the, to, they're used in every sequence. But you want to call those tokens to be the most informative tokens, right? They're just a popular word. So if every time I have to give a lot of attention to those not so informative tokens, is that correct, or it's just a bug of our method? We ask ourselves. So we're trying to observe how the tokens should what are the location of the tokens often show up in a single sentence generation, and experimentally we find our tokens are biased towards the window beginning. And this we're not alone in finding this observation. There are actually a paper in Stanford last year called "Lost in the Middle" shows a very similar phenomenon. They show that if they wanted to ask a language model to do a word retrieval task, the word retrieval task's quality will be the best when this word appears in the beginning or in the end of the document. But if the word appears somewhere in the middle belly of this document, the retrieval performance will be very bad. So that directly implies large language models' self-attention has a strong inductive bias to pay more attention to word in the beginning and the end of the context window, but fail to pay attention to the middle. That is also very natural if you think about how autoregressive attention is done. The first token is important because the first token is the base of generating the second token, the third token, the fourth token, until the last token. It's the most used one because it appears first. So no wonder self-attention would give it more weight. The most recent token may be semantically most similar token, so they also get a fair share of weight. So as a result, we see in self-attention, the first few tokens and the last few tokens are the most attended one, but if there are important information in the middle, they are lost. And we find that this bias also affect the heavy hitter as well. In fact, this pattern has also been heatedly discussed whether we should consider that's a feature or that's a bug. And some of our concurrent works tend to believe this is a feature to be utilized for efficient generation. For example, there was a special task last year people are very interested in called infinite length sentence streaming generation. Because typical LLMs are generalized very poorly for longer sentences compared to training sequence length. But if I want to generate very long, besides increase the training budget, there are also many people to discuss how to make already trained language model to just generate beyond the context length it has been used in training. For example, Llama 2 has a 4,000 token limit, but I want to generate 8,000 token document, what I can do? Well, recent works such as Stream LM and LM Infinite, they do that by just retaining they achieve that by just retaining the context windows initial tokens and the past tokens. So that's a very brutal method. You said I have a carry cache limit. Sure, I will just any token generated. I will always keep the first few tokens in the starting point of the sentence, and also keep the nearest tokens now just next door to me. And those are my whole context. I just don't give any care to the remaining tokens in the middle of the sentence. And this is directly motivated by this lost in the middle phenomenon. So this ad hoc policy has some success, but I have to point out they exhibit very clear failure mode. For example, in the retrieval task, or the retrieval task I displayed in search in the middle, in lost in the middle, those retrieve, if you want to find a word that only appears in the middle of the document, then you have no luck from this grouping method, right? Because you have dropped it totally. And if you wanted to do document question answering with details only appearing in the middle of the document, or you wanted to do summarization of the text, which you have to include the information in the middle, then such inference engine is doomed because they actively drop the middle. So we have tried to use our H2O method to compare with those naive token dropping method. So let's look at this figure on the top right. In Stream LLM, they are generating tokens in the, let's see, the frontier on the diagonal line. Let's say this is the token they want to generate. They will always keep the nearest token to this diagonal line to be generated token is this off diagonal line. And they will also always just keep the first few sentences in the generation. And as this token move away from the beginning, it will directly abandon the tokens in the middle. That's what Stream LLM is doing. And we just adapt H2O to exactly the same setting. When I generate this front-end token, I will adaptively select which token I look at. And we compare those two's performance. By the way, Stream LLM is one of the default engine in NVIDIA now. And not quite to our surprise, we find our adaptive token evaluation method solidly outperforms Stream LLM in the task I just mentioned. Multi-document question answering with answers in the middle. text summarization with a long text, and we are similarly able to stream H2O to generate an infinite length of sequence. And let me show you the demo we generate. On the left is the FlexGen engine without any cache handling, and you see it collapse very quickly. On the right is the same command, and we just keep generating without any memory cost because we are unlike evecting tokens. And you can see the generation speed is not affected at all. It's still that high throughput, so many text out. All right, and you can try this demo on my student website. And over the entire generation process, we also find H2O keeps consistently achieve lower perplexity, which usually means a higher quality compared to stream LLM, which only keeps the beginning and the end, the tokens. All right, so that have concluded one main part of the H2O work. I want to quickly talk about a follow-up work we did for H2O. That is to make H2O work with quantized large language models. Quantization is another popular way to reduce the model size and increase the throughput. But observation we had is the tokens selected by H2O are not necessarily suited for quantization. So if you want to apply the quantization to the KV cache, they could have lost performance. So our solution is called QHitter. It's a novel algorithm that combines both heavy hitter attention scores and an extra criterion called quantization friendliness to select which is important token at quantized models inference generation. And so we identify tokens that not only important for attention score as heavy hitter did, but also ready for KV cache quantization if we know KV cache is about to quantize. This work is called QHitter, a better token oracle for efficient inference with sparse quantized KV cache, and published in MLSys24 last year. And the result gain here is we can achieve now 20 times memory reduction and compared to uncompressed KV cache, and up to 4 times over the 3 leading engines we just talked about, and most importantly, 1.3 times further better throughput compared to H2O method we developed ourselves, again, without any performance degradation. So I can go relatively quickly on this work. So we find we just keep simple and use the simplest max min quantization with a per token dynamic range to quantize each token. So because this is the best supported on NVIDIA GPU, and I don't exclude the possibility that better quantization method could make QHitter works better. And we first look at how sensitive KV cache is to quantization. And here on those figures for 2 LLMs, you could find the quantization errors at different quantized depths, 8-bit, 3-bit, and 2-bit on each of the row. And in each of those figures, you can see the layer index from the lower level to higher level. Let me explain that. In this color, those colors here means the attention shift before and after quantization. So if you see a brighter color in this visualization, that means the attention is more affected and more drifted by quantization. So clearly you can see 2 patterns. Number one, the heavier you quantize, the more affected the LLM are in attention pattern. That's not surprising. Number two, the attention pattern will be firstly affected in higher layers of LLM and then affected by lower levels as the quantization level goes deeper. So the higher levels are more fragile. But overall, quantization seems to have a big impact on attention. So proceed observation 2. How ready for quantization those heavy hitters we select in H2O are for if we are about to use quantization for KV cache. So here you can see those. Let's see the plot on the left. The x-axis is the accumulated heavy hitter attention score. And those attention scores, if you still remember, we want to keep those highest. And default number we often use are the highest 20%. So there on the x-axis, we want to keep those on the closer to the right as possible for every layer, right? But now we have an extra dimension called quantization error. That is, after we apply quantization of this token and its KV cache, how much difference, how much quantization error we will receive on quantizing this token and its KV cache is on the y-axis. So there exists, so if we combine x and y-axis, what do we want? We want those with high accumulated attention score from H2O rule. So we want them to be to the right as possible. We also want those to be low in quantization. So quantization has a minimum impact. So where we want as our sweet point, we want those on the lower right part of this axis. However, do we get enough samples for heavy hitter in this criteria? There are, of course, some nice and sweet heavy hitters which are naturally having smaller quantization errors. Those ones colored in orange. They are high in attention score. They are low in quantization error. So we're good. But the problem is those orange sweetheart do not have enough numbers to support effective KV cache, which is by default, we say 20% in H2O algorithm. If I want to reach 20%, I have to go further along the axis in the accumulated attention score and try to capture some of those. And some of those will start to enter the high quantization error regime. That is the conflict. If I want to include enough tokens in the cache, I will inevitably include some tokens that, although they are high in attention score, but they are also high in quantization error. So we should resolve this problem by proposing a simple fix. When we select the heavy hitter tokens, we will compute the quantized error in the meanwhile. And the heavy hitter's score will be adjusted by the quantization error score. So we are using a modified score considering both heavy hitter attention and quantization error. And that will change our selection pattern. On the left here would be the selection if we only use heavy hitter because we merely consider the accumulated attention score. On the right is the selection. By the way, the selected tokens are colored in the green. On the right will be the selection that have jointly considered accumulated attention score and quantized error. So you can see that we made some compromise. This part of tokens, although they are very high in attention score, they're sufficiently high in attention score, they are also too fragile to quantization because of high quantization error. And we decide if we know the KV cache is going to be quantized, they are not our best friends. So we were giving it up and adjust our selection from this region to this region. This is a compromise to quantization. Q-hitter then did basically the same autoregressive generation pattern with a heavy hitter, except we include an additional quantization score in the score computation stage, and we find that using quantization of 4-bit or even 3-bit, Q-hitter could still achieve substantial performance. And over both the quantized only model and the heavy hitter model without quantization. And the performance increase sometimes are very drastic. For example, you can look at this one. It's on CNN Daily Mail dataset, Llama 2 chat, and with a 4-bit, with 4-bit, and this is a text summarization task. So we are able to improve the performance compared to the heavy hitter non-quantized version by, I don't know how to say, it nearly doubles the absolute performance. And in relative performance, I think it's nearly 80%. And more also interestingly, we find heavy hitter performs better than, Q-hitter performs better than heavy hitter in paying attention to tokens in the middle. We suspect that is because quantization error does not have the attention accumulation effect spirals towards the beginning tokens. It's more uniformly distributed over the entire token. So this is the inclusion of quantization error as a metric actually implicitly bias us towards the middle of the token back, which is sometimes very good for summarization task. And that explains some very big gains you see here with including the quantization error besides the efficiency. And similarly, we have justified that our performance, we have higher throughput, lower memory usage, and we can do the same long context inference, or up to infinite length strings. All right. So up to the so I'm near the end of my talk, but I want to throw some open questions for researchers of common interest. And those questions are all very close to my heart too. So I also look forward to more exchange of ideas and potential collaborations on those topics. I have the following questions hanging on my mind. First, I'm still not very sure if heavy hitter sparsity is a feature or a bug. Like we discussed, the tokens in the beginning of the window receive high attention scores just because they appear in the first of the sentence. And some of the tokens and some heavy hitter tokens are not informative at all, just because they are common popular English words. So should we do some kind of normalization to mitigate that effect? I don't know, but I tend to think so. And it's when we do the work, we are very when we did the work almost 1 year ago, we are also very uncertain if this observation will scale up to larger future models. So based on our testing so far, it seems to still hold. We haven't tested the Llama 3.1 405 billion parameter yet, but for the newer models, or after this paper is published, we see this observation still hold. And there is also a debate between should I intentionally attend more to the tokens in the middle of the window, and how. You see that the quantization arrow as a metric bias more attention back to the middle of the window, but that is more a coincidence than an intentional design. So should I do that intentionally? And how to leverage this token sparsity, attention sparsity property for more efficient training, either training from scratch or parameter efficient fine tuning. And lastly, as now people seem to be again obsessed with the state space models, we are also yet to test if this observation also hold meaningfully on state space models such as Mamba. And just a final remark. So our team has been continually working on this direction, how to find the low dimensionality structure such as sparsity and low rank in language models, attention, activation, weight, and gradient. One related work after heavy hitter is our ICML paper this year. I don't want to go through detail, but the title is Lococo, Dropping Convolution for Long Context Comparison. In this paper, we further discovered a bug in heavy hitter, which is if you have to drop tokens online continuously, then the token T and the token T plus one may have critical differences in what token they have selected, because you don't know what you are dropping, right? They must have non-overlap in their support set. Sometimes that causes sentence breakdown and discontinuity. We propose to further ensure better the selection continuity on the generation by introducing convolution. And essentially, that will make our language model in between a transformer and a state space model. And we can show further performance gain on top of a heavy hitter and a Q hitter. So I would encourage you to explore, and I look forward to discussion with you. And that should conclude my talk today. And welcome to check the associated codes and others in our GitHub, and I can be reached out by this email. Thank you for your patience.
Thank you very much. So, questions, please. Okay, let me start and let the other people think about their clever questions. I was looking at your observations, at your open questions, and the rest of the stuff in the evolution of the heavy hitters and beyond. Yeah, exactly. This is the context. And it very often resembled our open questions on the way of optimizing terms discovery in domain-bounded professional corpora. Have you ever thought of trying adding an intermediate step of term discovery and extraction, which might help you decrease the key value cache by orders of magnitude?
let me try to understand your question. Do you mean that I could extract some patterns from the path from the attention, so I could just use those past patterns instead of online deciding those patterns? Did I get your question right? Sorry, the voice was a little bit broken.
You are looking at all the possible tokens which could be found in texts about trading and text generation by large language models. I'm suggesting to look at specific tokens which are domain-bounded terms, which compose a terminal used in the community. So if you restrict yourself to a certain domain or a certain community, deep learning, for instance, then you might shrink your key value size even by the orders of magnitude. So it would be even better performance in terms of memory savings and latency.
Well, I see your point. Yes, if I use some keywords as landmarks, yes, it's totally possible I have a better selection. And I could even, if I know what keywords are my landmarks, I could have even pre-processed my question before sending it to the language model, right?
Yeah, exactly.
Yeah. I think that's totally possible. We didn't go that direction, but for people practicing language model efficient inference in specific domain, I would think that's actually a good opportunity for a product in some domain specific question answering also.
In fact, yes, we do that for ontology engineering for scholarly domains based on the texts collected in scholarly publications for this.
Yeah, great. I believe that is the right way to go.
Okay, more questions, Alexei?
Yeah, thank you for presentation. You said that you're not sure that heavy hitter sparsity is a feature or bug. And my question, is it feature or bug of an architecture of LLM or data which LLM was trained? How do you think?
Well, I think it may be both. So let's start from architecture. I think first in architecture, you always think about how self-attention was constructed. It has a softmax to ask all the KV similarity to compete with each other, right? Because essentially, let me find that figure. Essentially, when you try to generate, essentially when you generate a score, you softmax will ask each row's attention distribution to follow a probability. So if you have some of the scores, some words to be social queens and associated with all other words, its attention score will be very high, and others will be suppressed. I think this self-computation property is one reason why we see sparsity. Actually, although softmax has been a de facto member since the beginning of Transformer, I see recently there were a paper from Apple try to replace this softmax with a sigmoid function on element-wise basis and no longer require each row to be a probability, the probability distribution adding up to 1. I haven't tried that model, but I think that may substantially change the attention sparsity observation. So that's one architecture thing. Another architecture thing is as I said, due to the nature of autoregressive generation. The reason we will often see the sparsity biased towards the beginning and the end of the window is, as I said, the end of the window is always the latest token, which are typically more relevant to a character. The beginning of the window has been reused the most amount of times because everybody next to that need to use that token. So it also have a high score. So the poor guys are only those in the middle. But this is only about the usage. It has nothing to do with its usage. And it's because my specific pattern of generating from left to right, autoregressive decoder style. If I'm generating, for example, using BERT encoder style, sentence to sequence, I'm pretty sure you won't be able to observe this pattern. So this is another architecture related thing. And then data level related thing. I think there, okay, going back to the co-occurrence correlation plot with heavy hitter property. Apparently, in natural language, when we in natural language, people's general conversation, there are more common words used by the greatest population, but they don't mean anything related to important information. As Vadim just correctly pointed out, if I'm changing the domain, for example, from our daily conversation to a more specific domain, such as the papers you and I are writing, I'm pretty sure the common words you are using paper writing would be very different from the common words you use in daily conversation. Then which word will be the heavy hitter if your LLM is dedicated to generating a professional paper? I'm sure that will change as well. And not to say, as I already mentioned, the co-occurrence with the other word itself is only a very rough metric about how important this word is. So I think this sparsity thing, besides those are all reasons for contributing to the attention sparsity. Besides some obvious reasons, such as the model is so large, the representation space is huge, and it's nature that every word is only relevant and activate some of those neurons. This is a natural consequence of over complete representation as well. So I really think this is a compound question.
Thank you very much. More questions, please. Okay, let us thank Atlas once again for his very inspiring talk. Thank you very much.
All right, thank you for having me, and thank you. Bye.
We enjoyed it indeed. So
yeah,
goodbye and keep in contact.
Bye.
Cheers.
Bye.